Hello, my name is Mingi Ji, and I'm going to talk about our paper, Show, Attend, and Distill, Knowledge Distillation via Attention-Based Feature Matching. This work was conducted with Byung-ho Heo and Sung-rae Park. The presentation will be proceed in the following contents. First of all, let me introduce the concept of knowledge distillation briefly. Main objective of the knowledge distillation is model compression. Knowledge distillation mainly utilizes of transferring the teacher's knowledge to the student. Then, what is teacher and student network? Teacher network means the relatively cumbersome model that shows good performance. But the teacher network requires large amount of computation, so it is hard to apply for deployment to some service. Therefore, literatures introduce the student network that is appropriate to deploy for the service in the view of efficiency. But if we train the student network from the scratch, the student network shows not enough performance to deploy. So, knowledge distillation utilizes the knowledge of the teacher, that is from the intermediate output or the label prediction of the teacher. The knowledge is transferred from the teacher to the student, and student shows better performance than training from scratch. Then, what is knowledge? Following the literatures, there are three types of knowledge of the teacher network. First is feature, that is output of the intermediate layer of teacher. Second is output of penultimate layer. It is vector, and feature is tensor for vision test. Last is output probability, that means the prediction. This concept is based on classification tests. For each knowledge, there is a lot of works to how to make distillation. But how to make link between teacher feature and student feature is rarely considered. Now, let me talk about motivation of our work. In general, when distilling the feature of the intermediate layer, the link between the teacher layer and the student layer is manually selected. Usually, the manual link is connection of last layer of each blocks of teacher and student. See example of this page. But we thought that there would be a way to distill the teacher's knowledge more effectively through a meaningful link than a manual link. And we studied about how to identify the effective link from the data. And in general, only the final layer of one block was selected as the target of distillation, but we considered whether there would be a way to distill the teacher's knowledge from as many layers as possible. Let me briefly explain our research again. We aim to distill the knowledge that can be expressed in each layer of the teacher to the appropriate student layer among possible links. There is existing work that studies about how to learn where to transfer the teacher's knowledge. But in existing work, each meta-network identifies the importance of each link. So, relationship between whole links is not well covered, and there is limitation that a lot of computation is required because of the Hessian computation process. This is our proposed model, Attention-Based Feature Distillation, AFD. We model the feature linking methods through an attention mechanism. Teacher feature identifies the similar student layer and transfer more knowledge to the specific student layer. Because of the computational efficiency, our proposed model even considers all the links between teacher and student features. But AFD has the advantage of being computationally efficient compared to existing methods. And similarity-based learning allows us to better understand the characteristics of the model. After all, AFD's objective can be said to train which link is effective to distill based on similarity between the student features and teacher features. Now, I will explain the methodology with more detail. To learn the similarity relationship between the teacher feature and the student features, we use a vector from the output of lower average pooling on the teacher feature as query of the attention mechanism. And we set key from the student feature in the same way. And the intensity of the link alpha in this page is obtained from that product of query and key. Finally, for actual distillation, we use the existing attention map distillation method. So, the training and distillation of the intensity of the link is performed according to the equation LAFD. Since the trained alpha is calculated from the teacher query and the student keys, it has the characteristic that one teacher feature determines how much distillation will be made across all student features. Training loss is obtained by adding AFD loss to the classification loss, and logic-level distillation is also used for actual learning. Now let me talk about experiment results. First of all, I will start with the result of the qualitative analysis. This figure shows the distillation results for 3 situations. Each figure is the result of trained link. Yellow square means the intensity of the link is large, and purple square means low intensity between feature links of student and teacher. Manual link refers to the link used by the existing feature-level distillation model, such as attention distillation or FinMap. Compared to manual links and attention-based link, attention-based model shows various linking results. Also, it shows how our model learns by changing the link across the training effort, and the final link is different from manual link. Next is activation map. This is a comparison between ATT model that is based on manual linking and L2T and AFD, then using a learning-based link. Layers marked with the same color indicate which student layers link from the teacher layer. Manual linking-based ATT and learning-based L2T and AFD all show different links, and the actual feature map also shows differences. The red box shows that AFD receives distillation from the teacher's deeper layer, and the feature activation differs from ATT and L2T. The activation of the main object is higher. Also, we did quantitative analysis with model compression and transfer learning tasks. For model compression, we experimented with various architectures and datasets. The results show that Our methodology performed better than existing distillation methods on various datasets and networks such as Cyper100 and TinyImageNet and ImageNet. Also, we follow the setting from the L2T paper for transfer learning. For transfer learning, we use pre-trained network from the ImageNet, and we use pre-trained network as teacher. We obtain better performance than other models, including L2T on various datasets except Stanford Doge. To check the effectiveness of our linking method, we compared various linking methods and AFD methodology. Candidate layer means the targeted layer for distillation. We divide teacher candidate as random or equal interval. If possible teacher candidates are the layer 1 to 9, then example of random and equal interval of teacher candidates are on the slide. Also, we experimented random linking, ordered linking, and pre-trained AFD linking and proposed model. The example of each linking method is explained on the slide. Random linking does not consider the order of ordered and ordered linking follows the order. AFD pre-trained fixed the pre-trained linking of AFD network. First, the random linking showed poorer performance than the method of manual link such as ordered link. And learning the link through AFD showed better performance than the case of aligning the teacher and student features by specifying the order according to the depth. Finally, changing the link while training through AFD shows better results than fixing the link from beginning to the end of training by using the link information of the previously learned AFD. Last, we experiment with various number of candidate layers. With this experiment, we analyzed the impact of the number of teacher and student candidates. For this experiment, the candidates are set as the output feature of the residual blocks that are sequentially equidistant between themselves. We can see that when the student candidates are more than half of the total features, and using all teacher features provides better student performance. On the other hand, with the small number of the student candidates, using all teacher features causes an information bottleneck and degrades the performance. These experiments provide the guidance to choose the number of the candidates. This is the conclusion. In this study, we propose a methodology to learn the intensity of the link, which determines the degree of distillation between the features of the teacher and student based on attention mechanism. AFD has been shown to train the feature link effectively, and through various experiments, we analyzed the effectiveness of our proposed methodology.